In this video, we're going to talk about the physical pendulum. So what is a physical pendulum? We have an arbitrarily shaped rigid object. So we have a rigid object. It has mass m, and it is pivoted at point O. It has a center of mass located at a certain position Cm, as shown in the figure here, so that the gravitational force will appear at the center of mass. The pivot point O to center of mass distance is d. And I call the moment of inertia with respect to this pivot point for rotations around a fixed axis going through the pivot point, I, that's with respect to point O, the pivot point. Okay, so let me concentrate on this scenario here. First of all, I call this axis the z-axis. This is the x-axis, this is the y-axis. Okay, and I see that there's going to be a torque, a rotational effect of this force around this pivot point. So I have to consider, in order to calculate the torque, r cross f. So if I draw a vector from the pivot point to the point of application of the force, this will be my r vector. And then I find that in this setup I have the angle increasing in this direction. So this is my theta hat direction, and this is my r hat direction. So this is the direction in which the angle is increasing. And if I take the component of the force perpendicular to the r vector, so that will be on this axis. So if I take the component of this force onto this axis, I'm going to get mg sine theta, because this angle is theta. It will be mg sine theta. Okay, and now I want to calculate the torque with respect to this point. So the torque is going to be r cross f. It is d r hat cross with minus mg sine theta hat, and r hat cross theta hat gives me k hat. So this is going to be minus mgd sine theta k hat. Okay, and I'm going to have the net torque equals to moment of inertia times alpha. That's Newton's second law rotational form. So minus mgd sine theta is equal to I alpha, because the rotation convention that I have drawn here is in this direction. I'm taking alpha to be in the k hat direction, so plus k hat direction. So this is, if you want to write it in vector form, this would be minus mgd sine theta k hat is I alpha k hat, right? So I can see that I need to have this minus sign here if the torque is trying to decrease the angle. Okay, and what is alpha? Alpha is the angular acceleration. It is the second derivative of angle with respect to time. theta double dot. So I find that the equation of motion is going to be theta double dot is equal to minus mgd over I sine theta, which is not in the form of simple harmonic motion, but for small angle oscillations, for small theta, that is theta less than 10 degrees or so, I can replace sine theta approximately with theta. That's using Taylor's expansion we have shown before. So theta double dot is equal to minus, roughly equal to minus mgd over I theta. Okay, so in simple harmonic motion, I need to have an equation of motion of the form x double dot is equal to minus omega square x, and that is in this form. So I can see that this equation of motion is in the form I would like it to be. So we can see that the angular frequency omega for these oscillations will be square root mgd over I, which is 2 pi divided by the period, or the period of small angle oscillations will be 2 pi square root of I divided by mgd. So that's the period of small angle oscillations for a physical pendulum. Now I want to check what happens if all the mass is concentrated at CM, the center of mass location. Then what would be the moment of inertia with respect to this pivot point O? Then I would become m d squared, right? So the period then would become 2 pi square root m d squared divided by mgd. So m's would cancel, d would cancel. I would have as an answer 2 pi square root d over g. Now remember, in the case of a simple pendulum, I had a period 2 pi square root L over G, and that's exactly what I'm getting here, 2 pi squared D over G. So if D goes to L, this becomes simple pendulum. So this is telling me that what I have done is correct. Now, if you have an arbitrarily shaped object like this and you want to know its moment of inertia with respect to a pivot point that you choose on this object, this physical pendulum, that's my second point here, this setup can be used to measure the moment of inertia. So I can measure the moment of inertia because I can measure the period of small angle oscillations with respect to a pivot point. Okay, let's quickly take a look at an example. We have a uniform rod of mass capital M and length L that is pivoted about one end and oscillates in a vertical plane. Find the period of oscillation if the amplitude of the motion is small. Okay, so let me take a look at this setup here. So I'm going to define the angle theta to be increasing in this direction. So this will be theta. In that case, this is going to be my theta hat direction, theta hat, and then I will have the r hat direction here. Okay, and this is my z-axis, this is my x-axis, this is my y-axis. So what I find here is that I have the gravitational force that is going to give me a torque with respect to this pivot point. And the next thing I noticed that here is that it's a uniform rod. So that tells me that d, the distance between the pivot point and the center of mass, should be equal to L over 2. And there's one more thing I know about this uniform rod with mass m and length L, that is the moment of inertia with respect to point O, a rotation axis going through point O. We have calculated before, it is m L squared divided by 3. Okay, so if I look at the torque that is caused by this gravitational force, I take the r vector from point O to the point of application of the force. Then I take the perpendicular component of the force here. So I find that I'm going to get, because this angle theta will be the same on this side, I'm going to get mg sine theta. Okay, so the torque I'm going to calculate here is r cross with f. It's the d in r hat cross with the component perpendicular to the r vector, that is mg sine theta in minus theta hat direction. The other component will give me no contribution, right? So I will have at the end minus mgd sine theta. And what is the cross product? R hat cross with minus theta hat here. If you use the right hand rule, r hat cross minus theta hat gives you k hat. Okay, so I have the torque in minus k hat direction. The torque that I'm causing is actually counterclockwise, but this is because of the way I have defined the angle. I have defined angle theta to be positive for clockwise rotations. Okay, so the net torque must be equal to I alpha, and this is going to give me again minus mg d sine theta equals to I theta double dot. Small amplitude oscillations, small theta sine theta can be replaced with theta approximately. So I obtain theta double dot is equal to minus mg d over I theta approximately. So my small angle oscillation angular frequency will be square root mgd over I. Now I can substitute for I ml squared over 3 and for d l over 2. So this will be equal to square root mg l over 2. 2 is here, ml squared, and then I'm going to get the 3 upstairs. So this L will get rid of this L, this M will get rid of this M, and I will be left with square root 3g over 2L. And this is 2 pi divided by the period. So the period of small angle oscillations will be 2 pi square root 2L divided by 3g. So this will be my final answer for this question. Okay, so basically, knowing this result, omega is equal to square root mgd over I for any setup where I have a rigid object that is pivoted at a certain point, I can use this result in order to calculate the angular frequency and the period or frequency of small amplitude oscillation.